Well, again, welcome everybody to the tutorial on HPCToolkit. My name is John Mellor-Crummey. I'm a professor at Rice University and lead the HPCToolkit project. A number of my colleagues are also attending this morning. And so feel free to ask live questions in the chat as I go along, and my colleagues can answer you in real time. And then we can have a bit of a discussion at the end. Okay, so first let me start with some obligatory acknowledgements. The HPCToolkit project at present is largely funded by the Exascale computing project, also with some supplemental funding from Lawrence Livermore and Argonne National Laboratory, and some corporate funding from AMD, Intel, and Total Energies. And then I also wanted to mention that this is not all my own work. This is the work of a fairly large team. So the HPCToolkit project itself is based at Rice University, and I'm the PI for that. I have a set of research staff on my team, Laxano Adianto, Mark Krentel, Will Fan, who are here this morning. Matt Barnett is a recent addition. I have a contractor working on the West Coast who's primarily working with the national laboratories. That's Marty Iskowitz. I have a collection of graduate students. And then we work very closely with the Dynance project at the University of Wisconsin, and Bart Miller is the PI on that, and there's several members on his team as well. And so just so you're not under the illusion, we're only partially supported by the Exascale computing project. This is a fairly large team. So for those of you who may not be familiar with the Exascale project, in case there are any attendees from the outside, the goal here is to build performance tools for the DOE's emerging GPU-accelerated exascale platforms. And so at present, there's the Frontier system at Oak Ridge National Labs, and it has AMD GPUs in it. There's the forthcoming Aurora system at Argonne National Lab, which is based on Intel processors and Intel's Ponte Vecchio GPUs. And then there's a third system that is expected to be delivered this year at some point, called El Capitan, which is at Lawrence Livermore National Laboratory. And this is based on AMD's MI300 APUs, which means that the GPUs and CPUs are in the same multi-chip module. And so this is the set of three systems that we're working with under the DOE Exascale project. And in the meantime, we're also trying to make sure that our tools work on systems with NVIDIA GPUs as well, because they're present in many DOE systems at the national labs that I've listed, as well as others. So in this talk, I will begin by describing some performance measurement and analysis challenges for GPU-accelerated supercomputers. I'll give an introduction to the HPCToolkit performance tools, going through their components and their workflow and how the user interfaces work. And then I'll show you how you can analyze the performance of GPU-accelerated codes with HPCToolkit with a combination of slides and live demos. The focus for the second half is going to be on live demos. I'm going to be demoing this on a system at Rice rather than demoing it on Crusher or the Sunspot system at Argonne. Presently, the Sunspot system is still is closely held, and I don't think I'm allowed to demo anything off that. So I'll be demoing on an AMD system that is at Rice that has MI210 GPUs, which is like a tile of an MI250X, which is in the Frontier system. And then after going through the examples, I'll describe our status, some known issues, some ongoing work, and then there's pointers to some resources, documentation, and software there for reference, so that when the slides are published, you'll have all the links, and I'll be happy to take any questions. So there are a number of performance analysis concerns for GPU-accelerated supercomputers. So One of the main things is that we're trying to measure computation performance, and the principal concern is keeping the GPUs busy productively, and for that you need extreme scale data parallelism. Other things that are important are data movement costs, both within memory spaces. So the CPU and the GPU have different memory spaces. And so we're concerned about data movement costs, both within the CPU space, within the GPU space, and between the CPU and GPU spaces. Also, internode communication, typically using MPI, but also some applications under the ECP project use the GasNet infrastructure and UPC++ as well. And so we want to be able to track internode communication, and then also I/O is an important part of large-scale applications as well. And there are many ways to hurt performance. And so in large-scale applications, you can have insufficient parallelism, bad load balance, serialization, replicated work, parallel overheads like synchronization. And then the hardware and execution model are rather complex. And so there's multiple compute engines with varying characteristics and capabilities. So the CPU and the GPU are very different. And so we need to measure them differently, and the performance concerns on them are different. And I mentioned already that there are different memory spaces for the CPU and GPU. They each have their own complex memory hierarchies, and importantly, they're different. And finally, when we're computing on GPUs, the model for computing on the GPUs is to asynchronously offload computations. And so that means that we're measuring asynchronous computations on the GPUs, and that complicates the measurement as well as the execution model that you have to deal with. So some measurement challenges are that there's extreme scale parallelism in these applications. And so if we introduce any serialization in our tools, that's going to disrupt application performance. There are multiple measurement modalities and interfaces that we have to deal with. And so we're using sampling on the CPU. I'll say a little bit more about that later. On the GPU, we get callbacks from the vendor's GPU runtime infrastructures when operations are launched, and sometimes when they're completed. And for NVIDIA and AMD GPUs, we also get a GPU event stream through something called an activity API. And so there are several different ways that we're measuring. We're either intercepting the GPU callbacks, we're monitoring the event stream, and we're sampling on the CPU. Now, when we were just measuring CPU programs a decade ago, we could control the measurement overhead by controlling our sampling frequency. That is no longer the case with GPU accelerated applications, because we can't control how often your applications are calling GPU kernels. And so because there can be so many kernel launches during a second, then that means that that there are very frequent GPU kernel launches, and that means that we better be measuring them with low overhead. Otherwise, we're going to incur a fairly high overhead for profiling that we can't control because we're intercepting all the GPU operations. Another thing that turns out to be a challenge for us is that we are beholden to what we can measure with third-party measurement interfaces. So tools can only measure what GPU hardware can monitor. And in particular, support for fine-grained measurement is essential to diagnose GPU inefficiencies. There's an application at Lawrence Livermore National Lab called Mercury, and it's a quantum Monte Carlo code, and it basically has only a single kernel in it. And so if our diagnosis is that their kernel is slow, that's not good enough. They really need to know where their kernel is slow and why. And so we need to be able to measure inside GPU kernels and be able to diagnose inefficiencies. And in order to do so, that requires that there be hardware and software support provided by the vendor, because we don't get to access the GPUs directly. So our tools can only measure what the GPU hardware can monitor, the GPU hardware and also the software stack. We use the Linux perf events interface for measuring applications on the CPU with hardware performance counters. also, this allows us to measure into the kernel and see what time you're spending in, say, drivers for your GPUs. In the past, we found that there was significant amounts of time being spent in NVIDIA's GPU drivers, and that they were spending a lot of time allocating pages and zero filling them. And so providing that feedback to NVIDIA was helpful because they were able to correct it in a future version of their CUDA runtime software. And so it's important really to have these hooks and be able to measure into the kernel in order to understand what's going on with the applications and provide feedback to vendors as necessary. And then finally, we have these GPU monitoring libraries from the vendors. And so we have this CUPTI, the CUDA Performance Tools interface from NVIDIA. We have the ROC Tracer and ROCm Tools interface from AMD. We have a tracing level for a tracing layer for Intel's level 0. And so all of these things are the ways in which we gather our information, and we can't gather any information if those libraries don't let us gather information. And so what they do and their implementation strategies and the APIs they provide are crucially important for what we can do as a tool. So some other challenges for GPU accelerated supercomputers is that we have to support measurement analysis of performance data across nodes. We have to analyze measurement data with large-scale parallelism, because if we're trying to measure large-scale applications, we can collect a lot of measurement data pretty quickly. And so we need to be able to analyze that, and you'd like that to happen quickly. So we have to use parallelism. Our user interface must support inspection of data at scale. And that means that we can't necessarily load all the measurement data into the user interface at runtime. We've got to leave the measurement data in the file system, or at least in the memory of the supercomputer, and then allow our user interface to inspect it from there. And then finally, we'd like to facilitate inspection of performance data on remote systems. And so if you're collecting gigabytes of performance data on Frontier or Aurora, you would like to leave the performance data there and perhaps run a graphical user interface to inspect it on your laptop and remotely access your performance data rather than copying it to your laptop, or running a graphical user interface over the network. So Rice University's HPCToolkit performance tools are designed to measure and analyze the performance of CPU and GPU accelerated applications. They're designed to be easy. They allow you to profile unmodified application binaries. They're fast. They support low overhead measurement, with the one caveat that we can't entirely control the measurement overhead associated with GPU kernel activity, because only your application controls the frequency with which your kernels are launched. And then anytime we use one of these vendor wrapping interfaces, there's an overhead that they incur for introspection into your kernel launches, and so we can't make our tools any faster than the measurement software that the vendor provides. Our tools are intended to be informative. They help you understand where an application spends its time and why. And so we use call path profiles. I'll say a little bit more about that in a minute, to associate metrics with source code contexts. And so instead of just knowing that you spent some time in matrix multiply, we would like to tell you the entire call chain, how you entered the particular matrix multiply that is causing you a lot of time, or the GPU kernels where you're spending your time. We also have the ability to collect hierarchical traces to understand the execution dynamics, and I'll show you how that works and why it's useful. And so our tracing is in some cases quite different from other tracing tools, because we let you see the entire calling context in which activity occurs. And that's true for both CPU activity as well as GPU activity. So our tools are designed for a very broad audience. They're designed for application developers, for framework developers, compiler developers, runtime and tool developers. We use our own tools on on our tools as well to help us improve their parallelism and performance for either analyzing application binaries or analyzing large-scale performance data. So the capabilities that we have in HPCToolkit at a glance, we can measure complex application programs on a broad range of platforms. And so we support x86 power and ARM CPUs. We support NVIDIA, AMD, and Intel GPUs. We can profile and trace CPU and GPU activity. We analyze application binaries to be able to relate performance information to your source code, whether it's CPU binaries or GPU binaries. We're analyzing them to be able to report performance data and associate it with functions, loop nests, inline code, etc. We attribute raw performance metrics to source code using mappings, and so we recover these mappings by analyzing the application binaries. We compute derived metrics on demand. We give you a spreadsheet-like interface where you can write your own metrics as functions of existing performance data, of pre-existing metrics that have been measured. And we also support interactive exploration and analysis of measurements with a graphical user interface. We provide code-centric views of the profile data, so you can look at your calling context top-down, bottom-up, and flat, and I'll show you what that looks like in just a bit. We support time-centric views of traces so that you can see how your execution behavior unfolds over time, and this is particularly useful for understanding load imbalance across nodes in the system. And then we have graphical views of metrics for context that allow you to graph across all of the contexts or across all of the threads or GPU streams in a program to see if there's load imbalance or anything like that. And you'll see that in the context of this tutorial. So I guess it's probably around the turn of the century now, around 2000 or so, we were building tools for profiling CPU applications. And this is our workflow. And we had 4 tools. There's HPC Run, HPC Struct, HPC Prof, and HPC Viewer. And so we've been using this set of tools for quite a while, I guess. The tracing came around about 2010 or so, but this has been for at least a decade. This has been the workflow that we use. So when we moved to GPU accelerated applications, the workflow changed only slightly. So we still have the same core tools. The only real difference is that HPC Run, which you use to profile your execution on CPUs and GPUs, this records the GPU binaries that were launched by the vendor runtimes onto the GPU. And so we record the binaries because we're going to analyze them along with the CPU binaries. And I'll go through the whole workflow and show you how this works. But it's interesting that we've managed to maintain largely the same look and feel with the same set of tools that we had for CPU-based applications. And so that makes it about as simple to use as it was before. So the first thing is you compile your application with your make files, with GNU Make or CMake, whatever you choose, and produce optimized binaries. Nobody really wants to analyze unoptimized binaries because the performance of optimized binaries is largely going to be different. So you compile and link your applications like you normally do. Now, the only thing that where you might need to do something a little bit different is if you're interested in having performance information at a finer granularity than the routine level. For instance, if you're interested in having performance information mapped back to individual source lines or to inline code, and then in that case, you'll need to add a -G flag for your compilers. And so in particular, since we're talking about GPU accelerated programs, it's important to understand how to control having the compiler record information that will enable us to map performance measurements that are associated with machine code addresses back to the source code. And so adding a -G flag is the way that compilers do that. They record line map information during compilation. They record other information about inlining and whatnot. And so you'll add a -G flag, and this can be added in addition to your optimization flags, and it should have little impact in terms of performance. Sometimes adding -G may make some slight changes in your application, causing it to use slightly different calling conventions, but for all intents and purposes, it shouldn't really affect your performance. For certain GPU compilers, say NVCC, you also have to add a -line info flag to tell it that you want it to record line mapping information when it's compiling and generating GPU binaries. And so, generally you compile and link the way that you normally did, except that you might want to add some flags into your makefile if you want information at finer detail than at the procedure level. So then the next tool in the toolbox is HPC run, where you profile execution on CPUs and GPUs. And so HPC run collects profile files that attribute costs to source code contexts, and it also collects trace files. And you see how the trace files look a little bit later. So what we do with any of our measurements is we associate them with full calling contexts. And so I'll show you what I mean by that in just a moment. So when we're measuring CPU and GPU accelerated applications, we're typically using sampling on the CPU, and the sampling is driven by either Linux timers or hardware counters. So we can count cache misses or the completion of instructions or stalls on the processor. There's lots of things that can be counted. Typical processors today have maybe 200 counters in them. We're intercepting callbacks when the GPU operations are launched, and sometimes when they're completed. We're monitoring an event stream for the GPU operations. The event stream on NVIDIA GPUs can also include PC samples, include machine instruction addresses where that have been sampled during execution on the GPUs. Also, another modality of measurement is that we use binary instrumentation of GPU kernels on Intel GPUs in order to be able to collect instruction level characterizations. So when we're running, what we're doing is we're attributing costs, however they're measured, we're attributing these costs in context. And so if we set up a Linux timer to interrupt us, say, 1,000 times a second, then what would happen is we would get a signal from the kernel that says now is time to record a sample, that the timer has expired, and we will get interrupted, and we will be at a particular instruction. Say we're in some routine C, when called from B, when called from A, when called from main. And so what we do is we unwind the call stack to determine where the timer expired, or where, say, a hardware counter overflowed, or also when a GPU kernel was launched. We follow the same process, which is we unwind the call stack to identify the calling context, or as we also call it, the call path. And so this is we get this chain of contexts for a single measurement. And then over time, as we're collecting multiple measurements, all of these contexts get put into a tree. And so you can think of this as the context at the top, say, represents main, and then maybe this represents an initialization phase, and then some sort of solve phase. And then there are various things that might represent, subphases in that. And so what we end up with is a tree. And it's a tree of calling contexts, and at each of the leaves, there's some measurement data, And so the measurement might be the cost of GPU and kernels that are invoked at this point. It might be the cost of cache misses that were incurred in this context. And so you can think of the whole output of our profiling as being a tree with weights. And that's going to be what we measure for every CPU thread, for every GPU stream. So in order to measure CPU or GPU activity, you launch your application with HPC run. So HPC run will load itself into your application's address space. And so if you want to measure GPU activity, you can say -e GPU, and then you can specify that it's an NVIDIA GPU, an AMD GPU. You're using the OpenCL runtime or the level 0 runtime. So over time, we're going to change this to say CUDA and ROCm, but for now, it's just NVIDIA, AMD, OpenCL, or level 0. And so those are the kinds of GPU measurements that we can take. And then you launch your application and have your application arguments as you would expect. So on Intel GPUs, not only can we measure the activity, the kernels that you're launching, we can also add instrumentation. And so you can give an option that says inst for instrumentation equals count latency or SIMD. So this is going to count instructions. This is going to approximately attribute latency to variable to instructions that have variable timings. And so typically those are memory hierarchy instructions, loads and stores. And also we can measure SIMD instructions. And so this is to characterize your use of the SIMD units, which are a big part of AMD and Intel's GPUs. So you can use instrumentation to measure one or all of these things at the same time. And so you just specify a comma-separated list of the instrumentation knobs that you want to use. On NVIDIA GPUs, we can use PC sampling on the GPU. And so you just say, I want to use an NVIDIA GPU and turn on PC sampling. And then you run your application with whatever arguments. If you're interested in tracing, then you can just add -t. And that will trace if you're measuring on the CPU and measuring on the GPU, then this will trace both the CPU activity and the GPU activity. You can use tracing in addition to PC sampling, but PC sampling in the instrumentation dilates the measurement costs somewhat. It dilates the application execution time somewhat, and so probably a trace is less interest when you're measuring with PC sampling or instrumentation inside the GPU kernels. So HPC run can be used with job launchers as well. And so if you're launching an MPI job, you can launch it with JS run or srun or AP run. And so the rule is wherever you put your application, then you put HPC run with its arguments right in front of your application. And so instead of launching your application, you launch HPC run, which launches your application. And that's the way to use it. So when you launch things with HPC run, it will collect and aggregate profiles on the fly. So there is a calling context tree per thread. So the diagram that I showed you, we're collecting a tree with weights per every CPU thread. There's a calling context tree for every GPU stream that we use to keep track of the calling context that invoked GPU operations. We collect instruction level measurements on the GPU, and we aggregate that on the fly as well. We collect CPU traces, a trace of call stack samples. So what we're actually tracing is the call paths where you were interrupted using sampling. And so if a timer goes off and you get interrupted in some routine, C when called from B, when called from A, when called from main, then what we're tracing actually is the full calling context where your sample event occurred. And then for GPU traces, we're tracing the call stacks that initiate GPU operations. And you'll see how that works and what that's good for in a few minutes. So another thing that is coming out in the latest release of HPCToolkit is that we're actually able to deal with Python wrappers. And so for a long time, we could measure Python wrapped applications with HPCToolkit, but what we would be measuring and attributing to was actually the Python interpreter. And that's not really the level that you want as an application developer. And so what would happen is we have some call chain, and I apologize for the fact that these are all reds. So we're like working our way down to a leaf. And so these all should be interior nodes. And what happens is you enter a Python context and you go through a series of frames, and then you exit the Python context. So maybe I'm calling into Python and then I'm calling back into C or C++. And what we do inside HPC run is we recognize that this is what's going on. And then we, instead of recording this whole chain that says what was going on in the Python interpreter, we map that back to context inside the Python program. And so this is a little bit different because normally we do all of this attribution at postmortem time. After the measurement data has been collected. And with Python, it's a little bit unusual because we need to use a Python introspection API in order to map it back to Python context. And so this is a case where we're doing this mapping at measurement time. And so this is a new feature in our forthcoming release of HPCToolkit, and we can use it to monitor PyTorch. We're planning to try it with TensorFlow, but I don't think any of my colleagues have tried that yet, and I certainly haven't. So, okay, so that's our measurement side. So HPC run is recording our profile files and our trace files. And so all of this is the profiles are these calling context trees, and they're basically like a tree of machine code addresses with weights on them that represent costs that are incurred, and the chains or the paths through the tree of machine code addresses, they represent calling contexts in the program. And then the trace files are associating trace events with program contexts as well. And so it's associating it with these call paths in the tree. And so that's true for the traces of CPU activity, and it's also true of traces of GPU activity. So the second tool in our toolbox is HPCstruct, and so HPCstruct analyzes CPU and GPU program structure. So it's analyzing optimized CPU binaries, and it's also analyzing whatever GPU binaries have been collected by HPC run. So when you launch an application with HPC run, it's collecting the GPU binaries that were offloaded onto the GPU. And so then HPCstruct analyzes the program structure information and records it in some files. And then we're going to use this program structure information, which is basically a mapping from machine code addresses back to source code locations, back to procedures and source lines and loops and whatnot. And we're going to use this program structure information to interpret the profile files and the trace files. So to use HPCstruct, what happens when you measure an application with HPC run is it records a directory of measurement data. And when we want to analyze all of the binaries that are associated with an execution, we just invoke HPCstruct on the measurement directory. And there's only one option, which is GPU CFG yes. And so what HPCstruct does is it recovers information about files, functions, inline templates of functions, loops, and source lines. And it does that in parallel. And so in parallel, we're going to analyze all the CPU and GPU binaries that were measured by HPCstruct. And by default, what we're going to do is we're going to use half of the threads that are in your CPU set. And so if you're running on a whole node that has, say, 48 cores and 2 hyperthreads each, then we're going to use 48 threads to try and analyze everything at once. And so for large application binaries at present, what we're doing is we're analyzing them with 16 threads. We've made our HPC struct tool itself run in parallel. And then for smaller binaries, for things that are smaller than, say, 100 megabytes, then we're just going to use 2 threads each, because there's a lot of things that get loaded into the address space of your program, a lot of shared libraries, a lot of GPU code. And so commonly we see 100 things has to be analyzed. And so using 2 threads each for small things and 16 threads for large things seems to work out pretty well. And finally, to avoid spending too much time analyzing these binaries, we cache binary analysis results for reuse in other executions. So when you're using a platform, your application's libc is not changing. The MPI library you're using is probably constant for most of your work. And so there's like lots of libraries, the ROCm runtimes, things like that, that are changing very slowly. And so whenever we analyze something, we cache it, and we also tag it with an MD5 hash. And so if a library does change, we'll notice that it changes and not use the cached binary analysis results. But what this means is that when you're in a workflow and you're repeatedly executing the same application, and typically only one thing is changing, whatever piece you're working on, whether it's the application or some support library, everything else is going to be constant. And so you'll just read all of the results out of your cache. And so that makes HPC struct generally fairly fast. So this one option that I mentioned, this GPU CFG, yes, this is needed only for analysis of GPU binaries for interpreting PC samples on NVIDIA GPUs. On Intel GPUs and AMD GPUs, we don't expect to need a special option. We'll just leave the binary analysis of the GPU binaries on all the time. The reason why we need this for NVIDIA is that it can be inordinately expensive, because NVIDIA did not provide us with a proper API. And so in fact, we have to run their command line tools, NVDisASM, to analyze the instructions and the control flow in the binaries. And because their tools often fail when given a very large GPU binary, what we have to do is analyze it a function at a time. And so they have a command line knob where we can say, analyze function 1, analyze function 2, analyze function 3. And so we have to repeatedly fork their command line tools to generate result files in ASCII and then parse them. And so it can be slow. And so we turn this off by default, and you can turn it on when you want it. It will give you more information because it enables you to understand how costs on the GPU map back to calling context on the GPU and to loopness on the GPU, and you'll see that in a bit. So, so now we have we've collected our program structure information. We have our profiles and trace files, and then we have these 2 tools, HPCProf and HPCProf MPI, which are responsible for taking the program structure information and integrating it with the information in the trace files and the profile files, so that we turn our performance measurements into performance analysis results. And so HPCProf is a utility that you can run on a single node. HPCProf is highly multi-threaded, and so if you run it on a node that has, say, 128 hardware threads, it will probably use 127 hardware threads to analyze your performance data. And so this can analyze small to mid-scale experiments, hundreds of profiles. But if you're profiling an application or on say, an Exascale system and trying to collect data on, say, thousands of nodes, then HPCProf MPI would be your tool of choice. So this does not mean that it's only for profiling data from MPI programs. What this means is that we've written a program that uses MPI, and it processes performance data by effectively running a copy of HPCProf on every node that you've launched it on. and then it's using multi-threading within the nodes in order to analyze the performance data faster. And so instead of doing it all sequentially, or instead of doing it all, you're just using multi-threading on a single node. Now we're getting multiple nodes involved, and so we can mow through a large number of profiles faster. So in order to analyze performance data for a modest executions, I said sequentially here, but really this just means on one node. This means using multi-threading. You'll say HPCprof on your measurement directory to analyze data from large-scale executions in parallel. Then you can configure up a launch command saying, like, I'm going to use 2 nodes, and I'm going to use 22 core node. I'm going to use 22 cores per task on a node. And then I'm going to launch HPCprof MPI, and I'm going to have it analyze the measurement directory. The same way you would say, have HPCprof analyze the measurement directory, HPCprof MPI is going to analyze the measurement directory. And so in the measurement directory, there's everything that we've recorded using HPC run. And when we run HPC struct on the measurement directory, it adds information about the program structure recovered for binaries. It adds in the measurement directory. So we're presenting all of that implicitly to HPCprof or HPCprof MPI. So you can launch these the same way that you would launch a regular MPI job, and this is just going to analyze your profile data faster. So then the last piece in the chain, so after we get our HPCprof or HPCprof MPI, takes the program structure, the profiles and trace files, and assembles them into a database, taking all of the measurements and mapping them back to source code with the aid of the program structure information. Then we get to use our HPC viewer user interface to present traces and profiles, and also graph metrics across the threads and GPU streams in the application. So here's the code-centric interface with HPC viewers. So there's 3 panes. There's a source pane that shows source code. There's a metric pane that shows whatever metrics you've measured. And so here we're just measuring time, but you can also measure things like cache misses or bytes transferred by GPU copies or seconds in GPU kernels. There's a bunch of measurement columns that might appear here. In the navigation pane, what this is showing is a calling context. And so this is the top-down view. And so we're seeing that the main program invokes this detailed calling context. So there's a top-down view of calling context. There's a bottom-up view. So for instance, if you find that your application is spending a lot of time in memcopy, then in the bottom-up view, you can say, okay, so memcopy is 40% of my execution time. Who's calling it, and how much cost do I incur in each calling context? It would be very tedious to track down all of the places where memcopy is called in the top-down view, and it's simple in the bottom-up view. And the flat view presents the flat view then just presents all of the contexts in the program at once, and so you don't care how they got invoked. So for instance, if you're working on some library, yes, it was called from multiple contexts, but if I've got multiple loop nests inside my code, I want to know how much time was spent in the first loop, how much time was spent in the second loop, that sort of thing. So the flat view allows you to consider the effect of all of the calling contexts together. And then there are some controls for metrics. So one of my favorites is the flame button. The flame button shows you hot paths. And so I can start up at the top where it says I'm spending time in program root. So this is the root of the program. So the program root calls main. And then I can just say, show me the hot path where I'm spending all my time. And then it's going to drill down and reveal the most costly call path in the application. And so it will drill down and it will show a series of children up until it gets to a point where the costs shatter and no child accounts for more than 50% of the parent's costs. And so then it will show you a set of siblings, and then you can select one of them and then continue by hitting the flame button again. The next thing, f of x, so this is for computing derived metrics. And so you can, as I said, you can use these spreadsheet-like formulas to compute metrics of your own from the performance data that we've already measured. CSV is for writing out CSV files of the metric data that you see in the user interface. And then when you're dealing with GPU accelerated programs, there's lots of columns of performance data. So especially if we're using PC sampling on NVIDIA GPUs, we can get maybe a dozen different kinds of stall metrics. And so we have inclusive and exclusive versions of it. So that's 20 some columns just right there. And so often what you want to do with the metric selector is to say, I only want to show a few metrics. And so you can hide some metrics, reveal some metrics, and so it can make it easier to work with a very large number. And then in the calling context view, so this is, I mentioned that we're showing a top-down calling context. And so the thing that's interesting here is that we're not just showing procedures. In fact, we're showing loops inside procedures. We're showing inline functions. So here's a real function. These green ones are inline functions. These are inline templates for Raja, an outlined OpenMP loop. And then in the outline code, now we have inline functions. And so what we get from using HPC struct is that we're able to overlay all of this rich program structure on our measurement data, and we're able to do that without incurring any additional runtime cost. And so all of these inline functions that we're saying here is that we know that we were at a particular program counter location, and that program counter location is, say, inside main. Well, with our postmortem analysis, we can find that actually it's inside main, inside a loop, inside a deep call chain of inline code where we're calling this function. And so we can identify that this call site is in this loop and inline call chain, and that happens postmortem. And so there's no runtime overhead for this detailed association. However, when you're working with template-based programming models, it can be very useful for understanding what's going on, because well, before we started this, the folks at Lawrence Livermore were telling us, well, my performance tool is telling me that it's spending time in vector.h when called from main. And it had inlined lots of the functions, and they had no idea who was using the vectors, and it made performance analysis very difficult. And however, if you can put in all of the context about the inline functions, then you have a hope of understanding what's actually going on. Okay, so this is our source code oriented view. And when we're measuring parallel programs across multiple threads, typically what we're doing is we're summing across all of the threads, and you get to see the sum of those costs here. That's why it says sum here. So this is summed across, in this case, I think it was 72 threads. When you're running MPI programs, it's actually summing across all of the threads and all the ranks and presenting you this profile that's the summary of all of that. If I want to see something like, for instance, I want to know how much time, say, every thread spent in this selected inline function across all of the threads in the application, across all the threads and all of the ranks, then in fact I could go up here and use this bar to say I want to graph this, and I want to graph a metric for this context, and I can choose the metric that I want to graph. And so you'll see that in the live demo. So one thing that the profiles do is that they collapse out the temporal behavior. And so load imbalance and serial sections are kind of invisible in profiles. And so what we do is we trace call path samples on the CPU, and we trace invocations of GPU kernels. And so what's going on is on the CPU, n times per second, we're taking a call path sample of every thread. And so for an individual thread, we have a series of samples. So we're taking a sample at say t, and t plus delta t, t plus 2 delta t, 3 delta t, 4 delta t, phi delta t. So we're taking a sample, and what this represents is the call path that we're sampling. And that you notice that they all have like blue at the top. And so that all means that, so this is the set of call path samples for a single thread, and then another thread, and another thread, and another thread. And we do this for every thread, MPI rank, and GPU stream in the application. And so all of them are spending time, they started their call chains in main, and then maybe it calls a run method, and then the run method calls it init, and then calls some sort of solve thing. And so then you can see that in fact, that at some level in the call chain, that there are some differences among the processes. And so then the way that we look at these call chains is we have a visibility plane, and you can raise and lower it and say, well, at the top level, everybody's in main. And then if I lower it down, I see that everybody's in the run method. And if I lower it down a little further, then I see actually there's some differences in time, where early in the execution, I'm in some init method, and then later I'm in some sort of solve method. And so I'll show you how that works. So here's a sample view out of HPC Trace Viewer. So this is for a CPU-based application called Flash. I like this figure just because of the structure that's revealed in it, and you'll see a little more in just a minute. So on the vertical axis, we have MPI ranks, OpenMP threads, and GPU streams. In this case, it's just MPI ranks. So it's an MPI only application that I measured. And then on the horizontal axis, we have time. So this is from the start of the application until the end. In fact, this mini map over here is actually telling us this represents all of the processes over all time. And what this shows us is that we're looking at sort of a narrow window in time during the execution. And so this is a time slice across all of the MPI ranks in the execution that is early in the execution, and the time slice includes all threads. And so at the bottom, there's a depth view that's showing the history of calling context for the thread or stream where the cursor is. And so here's a cursor, and this says we're looking at rank 93, and this is showing the history of the call stacks for rank 93. And so there are parts of the execution where rank 93 is just sitting in the same place. And so this can be while I'm sitting waiting for a reduction to finish, or I'm waiting for a barrier to complete. And then there are other times where the rank is quite active. It's involved in computation. And so in this selected cursor for rank 93, this says at the crosshair is at 86 seconds into the execution on rank 93. And then in this call stack pane, this shows us the complete calling context for that point in time at that individual thread. And I can click anywhere within this and say, show me what is happening at this time. And so it'll say, this is on, say, rank 91, and then it will show me the full calling context on rank 91 at that time, and I can click anywhere. And so what the color refers to here is whatever node is shown in the call stack. And so I can look at the call stack at different levels. I can look at it at level 1, and it would show pretty much blue everywhere that says everybody is in Flash. And then I can move down a level, and I would find that there's driver evolve Flash is like the right-hand side, and then init Flash is like the left-hand side. And so what we're showing here is these colors aren't a legend for what's going on the screen. In fact, these colors represent what is going on at this particular calling context. And so the red means a particular routine. And if there's any red here, that means that that particular thread at that point in time is inside this routine. And you'll see how this can be used a little bit more. And so the hierarchy of views is actually very useful for understanding what's going on with application performance. So I already talked about what the color is used for, and I already talked about the mini map showing you where you are in the execution. So here is a run where we're using the trace viewer to actually look at the behavior of our own HPC struct application. So we used 32 threads inside HPC Struct to analyze a 7.7 gigabyte TensorFlow library. And what this is showing is that we start off and it's like opening the the application and opening some shared libraries and performing some initialization. And then there's a very parallel phase where we have lots of threads that are active and they're actually parsing all of the information that the compiler has recorded that maps machine instructions back to source lines, and we could do this in parallel. Then there's kind of a barrier phase where we're waiting for the first phase to finish, and there's a little bit of load imbalance, and so one thread is running a little bit longer and all the other threads are waiting here. And so this sharp dividing line typically involves some sort of collective synchronization. And so this is like a barrier at the end of the first phase. And then there's some initial work to prepare for a second parallel phase. And then here we're parsing the 170 megabytes of text in the TensorFlow binary. There's a little bit of finalization, and then we're writing out all of our results. And so what this shows us is we're able to see what the temporal dynamics of our application are by using the trace viewer. So essentially here I used HPC run of HPC struct, and then I'm using the tools on themselves in order to get this sort of view. And so you can get the same sort of views for your own parallel programs. And so this is another view using the trace view to look at a large scale execution here. So we were analyzing data for 2K MPI ranks that were using 2K GPUs. The application was LAMPS. And so what we're showing here is not the execution dynamics of LAMPS. We're showing the execution dynamics of HPC Prof MPI, analyzing the LAMPS data using 1,000 threads and multiple MPI ranks. And so it's analyzing 38 gigabytes of data in 41 seconds by using massive parallelism. And so again, we're using our own tools to see our tools. And so you can see there's this center phase where we're analyzing a lot of the measurement data. Here, what we have, the IO is occurring in phases because we're doing a streaming out of core transpose that occurs in a number of different rounds. There's a reduction phase before where we're figuring out how all of the context trees related from the individual threads, how they all relate together before we actually started analyzing all the measurement data. So you can get these views for your own applications. I thought I'd just show you a few from our code to give you a sense for what you can tell. Now, you might say this sort of looks like madness, but actually you can get some statistics and find out whether you're spending a lot of your time idle or whether you're spending a lot of your time in locks. And so, in fact, it can be very useful looking at the statistics of what we're spending our time in certain phases. And I don't just have to look at the whole thing. I can zoom in on the center phase and say what's going on here, and then get some statistics about what's in here. And you'll see how to do that in a few minutes. Okay, so now I'm going to go through some case studies. So I'll give a live demo of measurement and analysis of Quicksilver, which is a proxy app for that solves a simple Monte Carlo transport problem. This is a proxy app for the Mercury code at Lawrence Livermore, the one that I mentioned that has a single kernel in it. And so like Mercury, Quicksilver also has a single kernel in it. And so in order to analyze Quicksilver, you really want to find out what's going on inside your GPU kernel. I'll show a few slides that shows some analysis we did of Pele-C, which is an AMR solver for compressible reacting flows. It uses C++, MPI, and Amrex. And then I'll show some live demos where we're looking at measurement data for games. And so this is an ab initio quantum chemistry package that's written using Fortran MPI plus OpenMP offloading. I have some data from some executions that was gathered principally during a hackathon. We're working with the games team to help them to figure out how to tune their application. And then I'll also show you a live demo collecting some performance data for DeepWave, which is a PyTorch-based seismic modeling code. All right. So without any further ado, let me just bring up my virtual desktop here. Okay, so I'm in my Quicksilver directory. So we have a series of tutorial examples. So here is this is HPCToolkit tutorial examples. So these are on the web and you can clone them yourself. So this is I'll provide a link to these at the end, but these are in GitHub/HPCToolkit, HPCToolkit tutorial examples. And so the way we have this configured is there's basically a make file and a set of scripts here. And then in this setup env directory, there's some setup files. And what it's showing here is that I have setup file for Summit, for Ascent, for Cori, for Vortex, which is a system at Sandia. And I think my colleague Will has made some adjustments here. He may have thrown away the old ones for Ascent and Cori, and has some for some of the other systems.
And Perlmutter.
Pressure and Perlmutter. Okay, so I am on a local machine called UFront, which is a machine that has both AMD GPUs. It also has an NVIDIA A100 in it. And so I'm just going to source the setup script for UFront develop. I'll just show you briefly what sort of thing is in it. What it does is it just sets some things for batch queuing systems in general. So this is designed to be run on the machines like Summit and Cori and Crusher at the National Laboratories. And then it has some setup for how things are being built. And so sometimes the builds and the runs have to be submitted using batch submission. And here it's all just going to get done locally with Shell. So I'm just going to source this, set up UFront develop. And this is actually going to module load a version of HPCToolkit that I have in my own development branch. Typically, when you're on a machine at the National Laboratory, the way we'll set it up is you'll use a publicly installed version of HPCToolkit if you download these examples. Okay, so now I source the develop script. So then I'll just say make build, and all the examples kind of work the same way. So it's downloading it from GitHub. Notice that in the build, it is supplying --line info saying that this is we're going to measure this on an NVIDIA GPU. So it's supplying --line info saying collect have the compiler add the line mapping information in the GPU binary, and then we're telling the host compiler to add the line mapping information on the CPU binary. And so now we have our executable built. And so then the next thing I can do is I'm going to say make run. And what this is going to do is it's going to run the whole pipeline. It's going to use HPC run to measure it, HPC struct to analyze the analysis result, the application binaries, HPC prof to analyze the measurement data, and then we can view it. And so I'll just say run here. It's going to run very quickly. And now we just started the analysis, and it said that it's copied these results from cache. And so libpthread doesn't change very often. And so I have an environment variable set up that says, here's where I'm keeping my cache, and you can look up stuff whenever you come across it. And so the math library, libc, all of these binaries are things that appeared in the executable during our run. So let's go back and see what the commands were here. So when the application got launched, it just said HPC run -o. That tells it to put it in this measurement directory. I'm measuring real time, so that's using a Linux timer to measure the application as it runs. I'm measuring on an NVIDIA GPU. I'm collecting traces, and here's the binary I'm launching. And it's that simple. So then the binary runs. We collect all our measurements as it runs, and then here we say HPC struct. I just gave it explicitly the option GPU CFG no. For NVIDIA GPUs, I don't need to do this. I could just say HPC struct and the default would be no. In the script, it was easier to change the default to no or yes, and so it's there explicitly. And then I just told it to analyze the measurement directory, and so HPC struct figured out what CPU and GPU binaries were there. It analyzed a GPU binary that we recorded. The GPU binaries are named with an MD5 hash of the bits that we've been presented, because what happens is at runtime, we get told that there's a GPU binary and it's in main memory, and we have no idea what it is. So we compute a hash code and we write it out on disk. If we're measuring an MPI program, everybody's going to try and write the same thing. And so the first writer writes it and everybody else says somebody else already wrote it, so I don't need to do it again. That's why we're computing the hash code, so that we only write each binary once. And then, so notice that we're also analyzing the NVIDIA JIT compiler, because this is also something that runs at runtime. And so HPC struct just figures out what we've measured and analyzes all of the binaries so that we can map the measurements back to source code. And then finally, we say HPC prof and tell it to write this output directory, and then using this measurement directory as input. And so now we have all of our performance analysis results. So let me just run one more. I'm going to run a PC sampling experiment. And so just a different argument to this makefile. It's going to launch it again. Now it's using NVIDIA's PC sampling, gathering some different data. And now this time I said GPU CFG yes. And you'll notice that, let's see, the GPU binary here, it says is 381K. And so the analysis finished pretty quickly. On some of the systems at the national labs, we've encountered GPU binaries that are almost a gigabyte. And so those can, with 40,000 functions. And so if we have to repeatedly run a command line tool on each of those 40,000 functions, it can take much longer than you want to wait. And so a good answer for that is you don't set this flag, you don't use this flag if it takes too long. And if it's taking too long, you can just Control-C and then run it without the flag. But you only need, you only would want this flag if you've collected PC sampling data, which I have in this experiment. And so this is analyzing the binary and the GPU binaries and collecting detailed information on the GPU. Using HPC prof, I'm just applying it the same way to the measurement directory, to whatever measurements are in there. And then I'll show you the way that we launched HPC run on the application. So this is saying HPC run-O, put it in this directory that has -PC for PC sampling. I said that -E for the event GPU equals NVIDIA, comma PC, saying, so normally I would just say GPU is equal to NVIDIA if I want to measure the kernels and data copies and things like that. But if I want to do PC sampling, I just specify this one extra knob and then launch the application. And so that's it. All right, so now I can look at the measurement data. So the makefile is set up here, so I can say make view, and it's just launching HPC viewer, which is on my path to look at the measurement data. And you can see that there's something here that says some nodes have been elided. That's because I actually have some filters set up saying that if things are inside MPI, elide all the descendants. Just don't show me the details of MPI. Just show me the MPI calls themselves. And if you're inside Lawrence Livermore's Raja library, which is not being used in this application, but this is a template library, just throw away all the Raja nodes because we don't really want to see them. Okay. So that's what it's saying, that certain nodes are being elided in the measurement data. And so if I look at a trace of this, what this is showing me is I have here, this is a CPU thread. And so this is showing me the CPU thread over time. And then this second thing says is a GPU context. And so this says GPU context 1. And so this is showing me a sequence of activity over time. Now, I can look at this, and so it's so all of these things are recorded as call paths. And so at the top, if I'm looking at it at depth 0, it says everybody is in program root or things root called. Well, this is sort of artificial. So I can move down and say it's in main or things main has called. And then I can move down one more level. And so now it says cycle tracking Monte Carlo. Well, what is that? That's where my cursor is. So I'm inside cycle tracking Monte Carlo. That's this green color. And if I move over here, it tells me that's cycle init. So we're alternating back and forth between cycle init and cycle tracking Monte Carlo on the CPU. And then on the GPU, we find that we're only executing operations on the GPU during cycle tracking Monte Carlo, and that's why there's nothing here that's going on during this phase when we're in cycle init. And so the way to use this user interface, this hierarchy, this call stack hierarchy, is you look at the highest level that seems to give you some insight. And so immediately here, what we can see is that the GPU is idle during any time that cycle init is active on the CPU. Now, if I want to look deeper here, I can actually find out what is going on the CPU during cycle init. So let me just zoom in here on say 2 iterations here. And so so now we have a series of things that are happening between the GPU kernel execution. So this is on the CPU thread, and the GPU is active till here, and then it's idle. And so I'll move up one level. And so what this shows is that there's a pretty sharp dividing line that cycle init is active pretty much during the time that the GPU is idle. And then I can go and see that cycle init actually consists of, it calls Monte Carlo source now, and then population control, and then roulette low weight particles. And then I can look down at a deeper level and find that in fact there's some subphases inside. So inside Monte Carlo source now, there's other things going on. But for this analysis, actually at the high level, what we can find out is that there's no GPU offloading during cycle init. So if we want to improve the efficiency of the program, ideally, we would like to not have the GPU idle. So if some of the work that's being done here could be offloaded onto the GPU, then we could potentially make the application faster. Now, over here, what we're seeing is there's only one thing that's active on the GPU. There's only cycle tracking kernel. That's it. So the only kernel that is being invoked on the GPU is cycle tracking kernel, and you don't see any data copies in and out. And the reason is that it's using implicit copies. And so so it's page faulting the data from the CPU, and so those copies are not shown. We would show explicit copies. So if you had copy in or copy out. So this is the way that you can use the trace view. I'm happy to take any questions right now. If you have any questions about what we're looking at here, or you'd like to understand something about the interface, feel free to just speak up. Okay. Feel free to interrupt me while I'm doing this. So I'm going to move to the profile view now. And we have columns that say, here's where I spent real time. Also, I have a column for GPU ops. So this is a synthetic metric for GPU operations, and that's a sum of kernel execution times and data copies. And in fact, as I mentioned, there were no explicit data copies. So all of the GPU operations just represent kernel execution time. And so I can go and say, well, I'll select GPU operations and show me where the GPU operations are invoked. And so what this shows me is in a call path through, here's the main program. So it's highlighting the brace where the main starts. There's a loop on line 55. And here on line 58, it calls cycle tracking. And then there's a series of loops. And then at this point, it is calling a CUDA function. And so then that goes through a device stub, and we can see, in fact, that it ends up calling this CUDA launch kernel. And then we end up inside the GPU. And so we put this special marker here that allows you to understand where we're crossing from the CPU into the GPU. And then the thing that's being invoked, it's showing us here the first line in the function. That's because we don't actually analyze the source code. We're just analyzing the information the compiler has recorded, and it says that the first line of the function is line 128. And so this is the cycle tracking kernel that is getting offloaded onto the GPU. Okay, so that's our trace view and our profile view. So now I want to dip into, we'll look at the profile view with the PC sampling. And so for that, I'll just come back out here and say make view PC, which will just run the viewer on the performance measurement data that I've already collected and analyzed. And so in this case, we didn't collect any traces. And so one of the metrics that's up front here is GPU instructions. And I'll say, show me where you executed GPU instructions. And now you'll see something very interesting. So we have main goes through the same call path, goes into the kernel, and we see cycle tracking kernel right here. But also inside cycle tracking kernel, we now have detailed attribution of performance data. So we can see that on line 132, it calls cycle tracking guts. Okay, and here's the cycle tracking guts routine. And then on line 26 in cycle tracking guts, it calls an inline cycle tracking function. So we're analyzing the binaries for NVIDIA GPUs and recovering all of this information about inline code. And in fact, we're reconstructing calling context here, and I'll show you in a moment how we do that. And so inside this inline function, we can see that there's a loop. And so here's a while loop, and it calls collision event and so on. Okay, and so this gives us our top-down view, and we have a lot of detail about where we're spending our time in this kernel. And so of the 100% of the GPU instructions that are executed, we can see that here it says there's cycle tracking function, 73.5% of the instructions are in cycle tracking function, and then 18.9% are in this Monte Carlo load particle. And so what you can see from here, I can select this and say, well, what are you doing inside this? And it says, well, there's a bunch of inline functions, and it all comes down to where I'm executing a fair bit is actually is copying data. Okay, so so an interesting thing I can do is I can say, well, where am I stalling the most? And so this is GPU instructions, stalls of any kind. And so I can start at the top and say, show me where you're stalling. And it says I'm stalling a lot, 17.9% of the stalls, which is a significant fraction, is sort of started at the top and says, let's keep opening the call chain while any child accounts for 50% or more of the parent stalls. And so that brings us into this function, get reaction cross section. And you'll see inside this function, there's a GPU data access that's using multiple levels of indirection. And so knowing that this is going to involve multiple serialized memory accesses, where first we index by the isotope index and the isotopes, and then once we have that base address, then we can index the species, then we can index the reactions by the reaction index, and then get the reaction cross section. And so now, instead of just saying we're spending a lot of time in the cycle tracking kernel, in fact, we can see that, well, we're actually spending a lot of time inside this particular function when called from the cycle tracking kernel. So when you look at this in a little bit more detail, it's interesting because this is a way that you can discover opportunities for optimizations, because you can see here that we're indexing by isotope index and reaction index. But if we work our way out here, there's a loop, and it turns out that reaction index is changing, but in fact, isotope index is not changing inside this loop. And so in fact, if this were, instead of being a function that was called, if this code was inlined in here, some of the indexing that's being done, where we are, let's see, back here, where we're indexing by the isotopes index, this is loop invariant inside the innermost loop. And so in fact, if this could be hoisted out and we could index based on, we already knew the base address and didn't have to compute the base address on every iteration, then we could reduce the cost of this indexing. And so this is the sort of thing that you're probably familiar with doing on CPUs all the time. And now, because we were able to reconstruct all this detailed calling context and associate stalls with individual source lines and the full calling context in which they're incurred, then you can uncover opportunities for optimizations. So what am I doing in time? So I guess I'm close to running out. So I have a few more things to say. So so I have a couple of slides for Pele-C. I'll show you. Well, so we do some approximate reconstruction of GPU calling contexts in order to attribute the performance measurement data. I won't go through that here for Quicksilver. And so this is something that we do that nobody else does. And so even NVIDIA's tools won't give you this this calling context the way that we do inside NVIDIA GPU binaries. And our aim is to do this for Intel GPUs and for AMD GPUs as soon as we have hardware and software interfaces that will enable us to do that. So I'm going to skip the Pele-C example, but there's a slide here that shows how we've identified that that there are some costs incurred at a particular context, and by changing the way a lambda function is called, we've identified some opportunities for performance improvement in Pele-C, and then the application team submitted some changes back to their infrastructure. We've also been we've been using the instrumentation on NVIDIA GPUs, in fact, to show how much time is actually spent in indexing operations inside AMREX. And so about 23% of the GPU machine instructions are indexing these multidimensional arrays. And in fact, then another 18.3% of the GPU instructions are linearizing subscripts, where we're iterating by cell, and then we're coming up with IJK coordinates. So we recover IJK coordinates in one step, and it's pretty costly. And then we linearize those IJK coordinates to come up with a cell index. And so we've been discussing this a bit with the AMREX team and with the Intel compiler team. And we think that there are potentially some opportunities for the application to use perhaps a different interface in AMREX to avoid this delinearization, relinearization. And we also have been talking with Intel about perhaps improving their compilers so that, or the way that we're using it so that some of these costs can be avoided. It seems like a pretty high price to be spending 40% of your GPU machine instructions just doing substrate calculations. So this shows you the kind of thing that we can do, gathering GPU machine instruction measurements with Intel's binary instrumentation interface. So now I wanted to show you the games code, and since I'm short on time, I'm just going to go through some slides very quickly here. So what this is showing is a run on 4 nodes on Perlmutter, and we have an MPI rank, an MPI helper thread. All the things we see in blue are traces of some CPU threads. And then we have a GPU stream that's along the bottom. And so one thing that's very helpful is I can go up to this this filter menu and say that I want to uncheck everything. So so I'm not going to look at anything except for what I want. And then I say GPU, check all. And so this is going to show me just the GPU streams. And now I'm looking at the GPU streams across the 4 GPUs. And if I zoom in on a couple of iterations here, what this is showing is the sequence of GPU kernels that are executed. And you'll notice that for the selected kernel, in fact, there's a significant load imbalance across the nodes. And what was identified with this view is that there's a significant load imbalance for this kernel and for this red kernel. And when working with the games team, it turned out that they were actually partitioning triangular iteration spaces by just assigning an equal number of rows. And that's not the best way to do that. And so we worked with them and came up with a better scheme for partitioning these kernels. And so what this shows is actually for that kernel, for this J06 kernel, as they call it, this shows the load imbalance here. We can also see that load imbalance graphically by going in and selecting the J06 kernel and selecting and saying I want to graph it. And you can see that it's showing the running time increasing as we go from the lowest or GPU rank to the highest GPU stream. And so we've got this like linear increase, and that has to do with the partitioning of the triangular iteration space. So now this is the second execution where they worked on that to try and improve it. And so we go through the same way. And now we see, well, it actually looks a little load imbalanced than the other way. But if we select the J06 kernel, now the names have, the names have changed slightly because they encode the file and line number. So anytime you make any changes, it changes the file and line number, which changes the color. So that's a little bit disconcerting when using OpenMP offloading, that it changes the colors of the things that you're looking at. What we can see here is that, in fact, there's less load imbalance here than there was before. And that becomes more apparent if we actually graph that view the same way that we did before. And so previously it was ranging from 2 to 10, and now it's ranging from 8 to 6. And so there's less load imbalance. There's still a little load imbalance here. We've been talking with the team about how to balance the load even better, but this is a substantial improvement over what they had. So this is looking at a little bit larger execution with 5 nodes, 40 ranks, 20 GPUs on Perlmutter. And so this is showing both the CPU, GPU activity, the OpenMP threads. And so if we zoom in and just focus on just showing the GPU streams, now we see previously what we were looking at was load imbalance within a group of processes that were analyzing, splitting up the work for analyzing the same thing. And here they have multiple groups. And so there's groups of 4 ranks and 4 GPUs, and they're each working on some subset of the problem. But it turns out that this is working on a very a small subset of the problem and spends a lot of its time idle. And so when we spoke with the team, we said, actually, all of this GPU idleness, this is load imbalance, and that if you can distribute your work among the nodes a little better, then in fact, we could get much better performance. So they went back and they're currently redistributing their load manually. And so they adjusted their input files and came up with a much better load balance that reduces the serialization. And so the user interface sort of shows us that. So one of the things that we noticed was that there are gaps between, so there are gaps between the kernels here. And so the GPU is idle. So why is the GPU idle? Well, if we look in the gaps, we find that there's this yellow activity. And so if we zoom in, we find that, in fact, this is calling this routine mtar-br, which is calling Gaxby. And what this is doing is a symmetric matrix times a rectangular matrix. And the way that they implemented this was they did it with a bunch of vector operations. And so they did it on a single thread. And so what this is showing is thread 0, and we're looking at the time that we're in these gaps is spent doing serial execution of this function on thread 0. So we looked at the routine mtar-br, and you can see the Gaxby operations here. And so if they replace this with a call to dgem or a call to dsim, which is handling for symmetric matrices, then in fact, those have multi-threaded implementations, and those can use multiple CPU threads. In fact, there's like a whole team of OpenMP threads that are sitting there idle while this one thread is performing this vector computation. And so engaging the other the other threads to do this in parallel will be a lot faster. And then the last thing we did is we collected PC sampling data for games. And so we can see we're inside a target teams region, and we can work our way down and find that inside that, we're inside some function called inside this region, and then we're inside some loop. And then in fact, what we're doing inside this loop is we're doing a bunch of OpenMP atomic updates, and these are pretty expensive. They're updating, I think it's their FOC matrix using atomic floating point operations, atomic floating point updates. And so this is where they actually spend a lot of time in their calculation. This is something that really can't be avoided. And so there wasn't an opportunity for optimization here, but at least we could see how they were spending their time on the GPU. Okay, one more thing I want to show you. Deep Wave. Actually, since I'm a little pressed for time, I'm not going to show the live demo. So we collected data. So Deep Wave is built using PyTorch, and so we can see that there's a series of Python call frames, and then we go into the PyTorch infrastructure, and then there's some inline code that is generated by PyTorch. And in fact, we can come all the way out the bottom into CUDA code and see with PC samples. And so this is showing an application thread. So there's PyTorch uses two threads. So there's a CPU thread, another CPU thread, and then a GPU stream. And in fact, it's alternating back and forth between a forward phase and a backward phase, and we can see how the forward phase and backward phase interacts with these two threads if we zoomed in a little bit more, but I can't do that in the slides. And then finally, this is showing us from the same PyTorch example where we're now down on the GPU, and we're looking at stencil operations that are being performed inside the CUDA code. So we can see all the way from the Python all the way into PC samples in the GPU. So the status of HPCToolkit on GPUs is that on NVIDIA GPUs, we can collect heterogeneous profiles of CPU and GPU activity, including instruction level characterizations using PC sampling and traces like we've been looking at. On AMD GPUs, we can collect these heterogeneous profiles. The difference is that we don't yet have instruction level measurements within the kernels. There's no mechanism for that yet that has been provided by AMD. We can measure OpenMP offloading using the OMPT interface. And so you get OpenMP offloading, just like I showed for games, which was running on Perlmutter. We get the same sorts of views on Crusher as well. Intel GPUs, we can also collect these heterogeneous profiles. We can get the instruction level performance measurements, as I showed with Pele-C. We can see where we're spending our time doing subscript calculations, and we can get traces just like the ones I showed you for games. So there's some known issues. So on the AMD GPUs, we're using AMD's Rock Profiler and Rock Tracer APIs, and under certain conditions, HPCToolkit doesn't report the names of kernels because AMD changed their APIs relatively recently, and the initialization of AMD libraries is very order dependent. And so depending upon what the constructors in your application do, HPCToolkit may not get a chance to start monitoring before AMD's HSA library gets fired up. And once this library is fired up, then we've lost the ability to see the GPU binaries in it. And so this is something that we're working with AMD on. They now have a new ROCm Tools API, acknowledging that there have been a lot of problems with Rock Profiler and Rock Tracer. So in December, they announced this new ROCm Tools API. We've experimented with a little, but it's not wired into HPCToolkit yet. So this is something that's coming work. On Intel GPUs, we're using Intel's GTPin for instruction-based measurement. GTPin has been relatively reliable in the past, but with new GTPin and complex applications on Intel's latest GPUs, we've seen that GTPin has been observed affecting application execution. And so in some cases, turning on GTPin, and not just through HPCToolkit, just using Intel's GTPin interface directly, it caused some NANds to occur. So for some applications, we've been able to measure very effectively using GTPin. For others, we've reported this back to Intel, and they report that they have a new version that they're going to give us this week, a pre-release that reportedly addresses some of these problems. Then on NVIDIA GPUs, NVIDIA has a faster PC sampling API, and we've done a partial integration of that into HPCToolkit. This would reduce the overhead of PC sampling, which currently runs somewhat slower. But for lack of time and the focus has been on the AMD and the Intel GPUs, this work has not been fully integrated into HPCToolkit. So to finish up, we're working on improving the scaling, the analysis of machine learning workloads, working on support for remote data analysis, and our goal is to have, instead of just showing you measurement data, to offer some advice. So we built a GPU performance advisor for NVIDIA GPUs previously. It's not fully integrated into HPCToolkit, and so that's a subject of current work. And then for reference, there's some resources, and so HPCToolkit.org is your one-stop shop for the manual, for pointers to our GitLab repository, where there's a cheat sheet for how to download the software and whatnot. And I'll stop here and be happy to take any questions.
John, there is a question in the meeting chat, well, answered by Will, about how much improvement do you usually get?
So the improvement that you can get depends upon very much the kinds of inefficiencies that you have in your program. And so if you have significant load imbalance, like we saw with the games application, in fact, you could get a very significant improvement. And so we found improvements where changing a few lines of code might give 5% across an entire application, that changing a few lines of GPU code in an important kernel changes things dramatically. But other things like ensuring the load imbalance, like reducing load imbalance across MPI ranks or across GPUs, that can have very significant effects on performance. And so I expect that the larger scale that you're working at, the larger the improvements that you'll be able to discover. And so really, I guess I would throw the question back to you is, how inefficient do you think your program is? We'll help you find out.
Okay, I think we are running out of time, and it's time for the Tau people. It's ready. Yeah.
Okay. So we have a Slack channel, and we'd be happy to, you can join our Slack channel. And so we'll publish the slides. There's an invitation to the Slack channel, and you can join, and we'd be happy to answer your questions there. Thanks for your attention.
Okay.
And hope you found it informative.
Thank you. Now, Samir, you want to